Hi, my name is Maria Femayor.
Hi, my name is Gabriel Gonzalez.
I'm Valeria Sosa.
And I'm Matthew Spiteri.
Today we're going to be going over a few topics from Chapter 12 regarding turbo machines. To start off, I'm going to be discussing what exactly turbo machines are. They are a mechanical device where energy transfer occurs between the flowing fluid and a rotating element due to dynamic action. This energy transfer results in a change of pressure and momentum of the fluid, and this can be classified as either power producing or power absorbing. There are four components within a turbo machine as seen on this diagram here. The first component is a rotating element consisting of a rotor, runner, and impeller. As you can see here in the black and white parallel lines are the rotor vanes, and this is the rotating component that flows through in an electromagnetic system within the motor. The next part is a stationary element, which is a nozzle, and the nozzle serves to change the flow of the fluid within the system. There's also the input and output shaft, seen as like the inlet and exit in the diagram, and that's where the fluid enters. And that's all encompassed by a housing or casing that encompasses a turbo machine.
There are three different types of turbo machines. One of them being axial flow, the second one being radial flow, and then the third one being mixed flow. The difference between the three has to do with the fluid path in which it goes through in the axis of the machine. In an axial flow, the fluid path is parallel. So what that means is that if this was the axis of rotation, the fluid would go this way, parallel. Fluid is accelerated by the stator and decelerated by the rotor. An example of an axial flow would be a Kaplan turbine and some water pumps. In a radial flow, it's perpendicular to the rotation axis. So it would be like this. Fluid enters through the impeller chamber and the centrifuges forces draw fluid towards the center, causing energy of the fluid and its pressure to increase. So when water flows in, it starts to form like a circle at the end, meeting to the middle. And it kind of looks like a car engine piece of a turbo. And that's exactly what a Francis turbine is, which is that typical picture which you would think a turbo machine would be. And one of the interesting things about a radial flow is that there's less mechanical stress in a radial flow turbo machine compared to axial. So it's a little bit more efficient. In a mixed flow, it's the combination between the flow of axial flow and a radial flow. So it contains both components, both parallel and perpendicular. So in this picture, on the right, it's an example of an axial flow turbo machine. And on the picture on the left, it shows the difference between a stator and a rotor. And then, so just to recap, the stator is the one in which the fluid's accelerated, and then the rotor is what decelerates the fluid. In this radial flow turbine, on the picture on the left, it shows exactly what I mentioned before, which is when the fluid enters, it starts to form like a circle, and then it all goes towards the middle because of the centrifugal force, which is why it's sometimes referred to as that rather than radial flow. And then in this mixed flow picture, it shows you exactly what I mentioned in terms of the combination between the both. So the picture on the left is a radial flow, and it shows the flow of it being perpendicular. Picture on the right is the axial flow, which is just parallel, which goes straight through it. And then mixed flow is a little bit of a combination between both. So it goes a little bit parallel, and then it goes not 100% perpendicular, but a little bit perpendicular.
Now we'll go on to solve a problem relevant to this chapter. So our problem is a hydraulic turbine is to operate at an angular velocity of 6 revolutions per second, a flow rate of 10 feet per second, and a head of 20 feet. We're trying to solve for what type of turbine should be selected in this particular process. Why is this question relevant for us as chemical engineers? In the future, as chemical engineers, one of our main responsibilities will be designing industrial processes. And although specifications may change from industry to industry, a lot of these processes have to do with either harvesting power, where turbines will be a main asset, or using fluid to generate power, where turbines will be part of the bigger process. So what do we need to consider when selecting a machine? There's efficiency and flow rate. For efficiency, we have this equation, which we solve for power specific speed. This equation, we need to consider the angular velocity in revolutions per minute, the shaft power in brake horsepower, and then the actual head available in feet. So once we have this specific speed, we can go to figure 12.32. And according to our result, we will either get reaction turbines or impulse turbines. So we could get anything from rate of flow, mixed flow, or axial flow. And this is very important because we want to find a turbine that is good for specific process, that is efficient enough, and that won't make a problem with any of the other units. But besides this particular property, we also need to look at turbine design, testing, and industry experience.
So to solve this problem, step one is to identify the given information. I find it helpful to summarize the information we've been given so we know what we have and what we need to solve for. So we know that we've been given the angular velocity, the flow rate, the head, and that the fluid that's going to be flowing through this turbine is water. Our second step, we need to find the variables that we need to solve for the specific speed and the specific speed equation. So first, the easiest thing to solve for is the angular velocity, which was given in revolutions per second, which we need to convert to revolutions per minute, or RPM, which we can do as you see on the slide. And in doing so, we get a value of 360 RPM. So continuing to solve for the variables that we need, the next thing that we'll find is shaft work in horsepower. And we're going to do that following this equation that you see. This equation was defined in section 12.8.2 of the Munson-Young and Okishi text, which you can read for further derivation, but that's not really the focus of this problem. We're just going to apply this equation. So we need the specific weight of water, the flow rate, the efficiency, and the head in order to solve for shaft work. So we're going to assume an efficiency of 94%. We're going to use the flow rate and the head that we've gathered from step one. And the only thing that we need to solve for, or we need to in order to solve for shaft work, is the specific weight of water. And we can find that in Appendix B, Table B.1 of the textbook. And in doing so, we find that it's 62.4 pounds per cubic feet. So when we plug these values in, you get the shaft work to be 11,731 pound-feet per second. But the specific speed equation requires shaft work to be in units of horsepower. So following the conversion that you see on the slide, we can convert shaft work to be 21.3 horsepower. So lastly, next we can plug in the values for the specific speed that we found. Recall that we found the angular velocity to be 360 RPM, the shaft work to be 21.3 horsepower, and we know from step one that the head is 20 feet. And plugging these values into the specific speed equation, we get 39.3. And lastly, we can use the specific speed in conjunction with figure 12.32 of the text. And if you follow the red dotted lines, which are going to appear on the graph, you can find that for our specific speed of 39.3, they intersect at a point where a Francis turbine is going to be the most efficient. And now we need to know whether or not this turbine will be radial mixed flow or axial flow. So if you look above, you see that at around 39.3 specific speed, a turbine of mixed flow design will be the most efficient. So we know that given these design parameters, a Francis mixed flow turbine is the most efficient. And now we've officially solved this problem. So we've gotten all of our material from the Munson-Young and Okishi text. So if you have any, if you want to look further into our information, you can refer to that. And thank you all for listening.